Okay, so the plan for today is to finish up one last problem in mixture applications from 3.3, and then work through 3.4 solving geometry applications. The quote of the day kind of related to some of the stuff we've been talking about with money and interest rates and things like that. These can be kind of abstract. Like, what do we mean? What do we mean by an interest rate? Like, why do we get interest on money that we invest, or why do we have to pay interest on money that we owe? Um, I think one thing in our society today, maybe for quite a while, not just, last few years, but if we ask what is fiat currency, what is, a dollar bill, or really these days, what is an arrangement of electrons in some server somewhere that says that you have this amount of money, why am I willing to give up actual time and actual resources in exchange for slips of paper or, rearrangement of some electrons on some bank's computer? And I think if you ask a lot of people, you say, what is money? They might say something like, well, it's what enables me to get stuff. It's what enables me to exchange it for actual resources. But I think the first part of this kind of working definition of what money is, or currency, or fiat currency, is that it's evidence of past productive utility provided to the market that entitles you to future productive utility from the market. So a couple of things to maybe unpack there is, one, well, why should I get interest on my money? Am I providing something in addition to what I provided already? If I, did some work and got $100, if I invest that $100 for a year, why should I have more than $100 at the end of the year? What am I providing to the market? Well, I'm offering to defer my compensation. I'm offering to spend that money later, say a year down the road, in exchange to maybe allow somebody or enable somebody to spend that money currently. So I might lend it to them. Maybe, they had a shingle blow off of their roof and they really need to replace that quickly. They have much more urgency, and I just want to go out for a movie night with friends or something. I can postpone that. They can't really postpone their, fixing their roof. So that exchange is maybe something that they're willing to pay a little bit more to have access to that money earlier. I think that's always a good way to approach investing. If you approach investing as, how can I invest in order to get as much as I can? That's the kind of thought process that I think can lead you down a tough path, right? Like you can easily be convinced by some shady investment folks that this is a great investment because it'll double your money in 2 years or something, and it sounds great, but what value am I exchanging for that? Is somebody really willing to pay double now for what they could wait 2 years for? Maybe not. So anyway, that's just a thought on, when we're talking about simple interest or compound interest, whatever it is, just kind of a thought on, sorry, my allergies are like going berserk today. Just a thought on kind of what that means. Why should we get interest on investments or pay interest on debts? And of course, the other practical answer is, well, if I could just stuff $100 under my mattress, that's probably easier for me usually than going and finding a place to invest it, right? So you kind of have to incentivize people to take the time and the energy and the effort to do something to make this exchange. And also the person lending out the money, they do incur some risk. So if I stuff the $100 under my mattress in a year, it's going to be $100 still. If I lend it to somebody, well, maybe they aren't able to pay it all back, right? Or if I invest in the stock market, maybe the stocks go up, but maybe they go down a little bit. So I also want to be compensated for that risk. So if we want a higher return, if we want a higher reward for our investment, we need to exchange some kind of value for that. We either need to be willing to take on more risk to go into an investment that other folks aren't willing to go into, to invest for a longer period of time, something along those lines. To go into an investment that requires more effort and energy on our part, that's another example. Real estate is a good example of that, right? It's really easy for me to buy more shares of something like the S&P 500. It takes a lot more time and energy. It's much more labor intensive for me to go and buy a house and renovate it and fix it up to resell it or to rent it or whatever. Okay, so moving on to the last problem in 3.3, we have one lecture problem and one worksheet problem. And so this is wrapping up the mixture applications section. And this is a bit of a challenging problem. So here, let's suppose that we have access to two types of vinegar. We have cooking vinegar that we would, use to make, maybe balsamic vinaigrette kind of idea, although that would be balsamic vinegar, but like a vinegar and oil kind of dressing. So that vinegar is 5% acid by volume. We have access to cleaning vinegar that we would use to like clean out a dishwasher or something. And that is 7% acid by volume. So we have one, this is really the mixture applications question, but the first and the third question are kind of just general questions. These aren't necessarily, at least this first one isn't necessarily a mathy question, but it brings up an interesting point that I think is important to kind of know about for just general life, but also for applications in math. So we might look at this, and these are roughly like if you went to Walmart or something, or Giant Eagle, these are roughly what you would see. Probably a 5% vinegar for cooking and maybe 6, maybe 7% for cleaning. And I think a lot of people would say, well, why did I go through the trouble of having two different types of vinegar if the difference between them is only, say, 1% or only 2%? Why care about this? Does anybody have an answer to that? Why is, I mean, is this cooking vinegar at 5% and the cleaning vinegar at 7%? Are they basically the same level of acidity? They're only 2% different. Any thoughts on that? Well, this is.
I'm sorry, could you repeat that? Or is that a rhetorical question?
No, it's an actual question. Yeah, just this first question here is, why would a store carry cooking vinegar that's 5% acidity and cleaning vinegar that's 7% acidity? Why not just carry, cooking vinegar at 5% acidity and you can just use that for cleaning?
Because 5% acidity may be safe for human consumption, but 7% acidity may not be safe for human consumption.
Yeah.
There
So
could be
exactly.
that slight of a difference could mean that's, even though it seems like such a small difference, it's like probably not the difference between a cleaning product versus something that you can actually consume without hurting yourself.
Yeah, so I guess that's the question though, is if the difference is in some sense only 2%, is a 2% difference likely to take us from something that's safe to something that's not safe? 2% doesn't seem like a big difference. But if we said the difference is only 2%, really what the thing I'm trying to point out here is the difference between a percent increase, which we talked about, was it last class or the one before, when we were talking about the financial applications. So we were talking about the percent increase from, $1 amount to another versus percentage point increase. So percentage point increase, if I have two percentages, if I'm going from 5% to 7%, my percentage point increase, I've increased by 2 percentage points. Or in other words, if I was paying 5% income tax and then they raised the tax to 7%, and now I'm paying 7% income tax, I'm only paying 2 percentage points more in income tax than I paid last year. But what's the actual percent increase? Remember, percent increase is something like new minus old over old. So it's like, this is like new, oh, whoops. It's like new minus old. This gives us our percentage point increase. But the difference between that and percent increase is that denominator. So what's the percent increase from the percent increase in acidity from my cooking vinegar to my cleaning vinegar? It's 7% minus 5% over 5%. 5%, 0.05 is a pretty small number. If I divide by a pretty small number, that makes my fraction overall pretty big, right? Having a small number in the denominator magnifies this difference. So it's only a 2 percentage point difference, but here I get 2% over 5%, or 2/5, or 40%. So actually the cleaning vinegar is 40% stronger, 40% more acidic. There's a 40% increase in acidity relative to the cooking vinegar, even though it's only a 2 percentage point increase. Or another way of looking at it is if I had income tax, if I was paying 5% income tax on my income last year and they changed the laws and now it's 7% income tax on my income this year, the tax only went, or the tax rate only went up 2 percentage points, but the amount of dollars, if I made the same amount last year and this year, the amount of dollars that I would have to pay would increase by 40%. If I paid, $100 last year, I'd have to pay $140 this year. So percent increase and percentage point increase are very different. And I've been in meetings and things with, people with degrees in finance and, a lot of experience in finance, and they'll get these mixed up, right? So particularly when we're dealing with percent increase of things that are starting out as small percentages, things like tax rates or things like acidity, we have to be very cognizant of whether we're dealing with a percent increase or a percentage point increase. This increase in acidity represents a 2 percentage point increase, but since that's on top of a basis of only 5%, that gets magnified by, well, 1 over 5% is 20. That's 20 times. So it gets magnified by 20 times in our percent increase. So really the cleaning vinegar is much, much more acidic than the cooking vinegar, even though the percents that we see on the label seem to be very small differences, because our basis is such a small number that we're working off of. That difference is magnified. And of course, I mean, if anybody has worked with, I know there are some folks in science and nursing and in those fields, if you've worked with 100% vinegar, well, essentially the acid in vinegar is acetic acid. So if you worked with 100% acetic acid, glacial acetic acid, very, very nasty stuff. It's, so it's going from having 5% of it in a dilution to 7% is a very significant increase, even though it might not look like it on those two numbers. Or if I wanted to, yield, say, 12% return on my investment instead of 9% return, that doesn't seem like a lot. I'm just going from 9% to 12%, 3 percentage point increase, but my return that I want is 3 percentage points higher on a basis of 9%. I've got to get 30% better performance to get from 9% percentage points to 12 percentage points on my yield. So just a good thing to know in general, especially if you're going into anything that deals with like chemistry or mixing acids and bases, things like that, or if you're going into finance, things that like tax rates and returns, you'll see this difference pop up all the time. Percentage point difference versus percent increase. Two very different things in a lot of contexts. Okay, so onto the regular scheduled programming. How much of each vinegar should we combine if we want to make a 30 fluid ounce solution that is 6.2% acidity? Okay, so we have, let me get myself a little more room here. We have cooking vinegar that is 5% acidity. We have cleaning vinegar at 7% acidity. And we want 30 fluid ounces at 6.2%. Acidity. There we go. I can't spell it. So how much of each of the cooking and cleaning vinegars should I combine to make 30 fluid ounces of a solution that's 6.2% acidity? Well, let's let X be the number of fluid ounces of cooking vinegar and Y be the number of fluid ounces of cleaning vinegar. All right, so if I want a total of 30 fluid ounces, one of my equations is going to be X plus Y equals 30. The total number of ounces has to be 30 fluid ounces. I don't want to just start mixing stuff and then have a whole bunch of waste at the end, or start mixing stuff and not have enough at the end. So X plus Y has to be 30 so that I get the right final amount. But I also need the right amount of acidity. I also need 6.2% acidity. So if I have X fluid ounces of cooking oil or cooking vinegar at 5% acidity, I essentially have 0.05 times X fluid ounces of acid, fluid ounces of acetic acid in the mixture coming from the cooking vinegar. If I have Y fluid ounces of cleaning vinegar, then I have 0.07 times Y. That's the amount of fluid ounces of acid, of acetic acid, that I have in the mixture coming from the cleaning vinegar. So this is the total acidity of my solution. This is the total amount of acid in my solution. And I want this to be 6.2% of 30 ounces. My end solution, I want to be 30 fluid ounces at 6.2% acidity. So this is the amount of acid I want in my final mixture. Okay, so I have two equations and two unknowns. And I saw that my strategy before was to say solve the first equation for one of the variables, kind of plug into the second equation. So X plus Y equals 30, we can say, for instance, Y is 30 minus X. In other words, the amount of cleaning vinegar I need to mix in is 30 ounces minus the amount of cooking vinegar that I mix in. And then I can combine this piece of information with my second equation to make an equation in one variable, 0.05x plus 0.07 times 30 minus x equals, and then this right-hand side, this is just a computation. So let me just jump over to the calculator and do 0.062 times 30. And that gives me 1.86. Is that right? Yeah, 1.86. So that was a lot of setup. But at this point, I just have an equation in one variable that I want to solve. At this point, I mean, I did a lot of work to get these equations to boil it down to a single equation, but from this point on, I just go through my basic equation solving steps. Maybe the first thing I'll do, I have a lot of decimals. I see I have 2 decimal places in each term. Maybe I'll start by multiplying by 100, which will give me 5x plus 7 times 30 minus x equals 186. So I got rid of my decimals. That might make things a little easier. I can multiply out my left-hand side. I'll combine like terms. I'll swap these around and make this 210 minus 2x, just so I don't have that negative in front. Leading, I tend to be a little more likely to forget it if I do that. I can subtract 210 from both sides. And this gives me negative 24. And I see that x is 12. So this tells me that I should use 12 fluid ounces of cooking vinegar. And then what's y? Well, y is just 30 minus 12. I should use 30 minus 12 or 18 fluid ounces of cleaning vinegar. This will give me a mixture that is a total of 30 fluid ounces and that has 6.2% acidity. Does this kind of make sense? Yeah, sure. I mean, if we mixed equal parts cooking and cleaning vinegar, we should get 6% acidity, right? Right in the middle of 5 and 7. We want 6.2%, so a little stronger than that. So we need a little more cleaning vinegar than 50-50, a little more cleaning vinegar than, say, 15 fluid ounces. 18 seems to be in that ballpark. So this just kind of, it makes sense from that standpoint. Again, these applications, we can, when we have an application, not just an equation like this, we can use the context to help us check things at the end. So that's the solution. No pun intended. But that's the solution to the math problem. And then kind of 2 follow-up questions. So what are your thoughts if I had asked, if I said, okay, well, instead of 6.2% acidity, I want to combine these 2 cooking and cleaning vinegars to make a solution that's 30 fluid ounces with 8% acidity. Could I do that? Could I combine these 2 acids to make a solution that's 3% acidity? And if the answer to either of these is no, in one of these, is there maybe something easy that I could do, thinking a little bit outside the box to actually come up with the solution that I want. Any thoughts on this? Can I make a solution just combining these two that's 8% acidity or 3% acidity? And if not, then could I maybe figure out another way to make a solution with one of these acidities? Any thoughts on this?
I feel like we would just replace the 0.062 in the equation with 0.08 or 0.03 in order to find that out.
Yeah, so I mean, if we just, if we just jump right into it, that's what we would do.
Is that
But
what you were
let's take
asking?
a-
I'm sorry.
No, yeah. So that's procedurally what you would do. But the question is, we have a context here. Does it even make sense to ask this question in terms of the context? Okay. Can I combine a 5% acidity solution and a 7% acidity solution and end up with a solution that is 8% that is more than 7% acidity, or that's 3% that's less than 5% acidity?
Well, I don't want to sound silly, but I feel like we can't do 3% because 5 and 7 are higher than 3.
Exactly. Yeah.
Oh,
Yeah,
okay,
exactly.
okay.
And yeah, so that's exactly how we can use context to help us figure out, what's even possible. Yeah, so because if I used entirely cooking vinegar, that's the lowest acidity that I could get, quote, mixing these two, right? And that would give me 5% acidity. The highest acidity I could get, quote, mixing these two would be to just use cleaning vinegar and no cooking. That would be 7% acidity. The only acidities that I can achieve mixing these two are acidities between 5 and 7%. So realistically, I can't make an 8% acid solution unless I had a stronger acid sitting around. If I had glacial acetic acid somewhere under a fume hood or something, I could pour some of it in and super carefully and maybe do it. But just combining these two or using reasonable resources that a person might have in their house, I can't get above 7% acidity. So 8% is kind of not going to work. Now, thinking outside the box a little bit, this isn't really a math question, but could I get 3% acidity using kind of these two vinegars and things that are, reasonably common around a house?
I mean, you could dilute it with water. Would that change the acidity?
Exactly. Yeah. Yeah, exactly. So I could just, add some water that's like 0% acidity. So I could take, say maybe Z is water with 0% acidity. And I could, say combine my cooking vinegar with water. X plus Z has to be 30. 0.05x plus 0Z is 0.03 times 30. Because water has essentially zero acidity, and my cooking vinegar has 5% acidity. 3% is between 0 and 5%, so I can achieve that acidity. Now, is the water going to mix nicely and all that? That's a question we'll leave to the chemists. Am I going to actually be able to make a solution out of that? And we'll leave that to the chemist. But essentially, yes, we can take something that is not acidity, something that's a neutral pH, and just combine it in. And there are lots of things that exist, around the house that we could use to do that, and water would be the easiest one. So it's kind of an exercise. And you had hinted at this as an exercise. What if I just plug in 0.08 here, right? If I did 0.05x plus 0.07y equals 0.08 times 30, and x plus y equals 30. we know that in some sense we shouldn't get a solution. We actually will get a solution to this mathematical equation. It'll dump out a value for x and a value for y. So as an exercise, go through in your notes, solve this, these equations here, figure out what x and y you need, figure out what number of fluid ounces of cooking oil or cooking vinegar and number of fluid ounces of cleaning vinegar you need in order to make a solution that's 8% acidity. And then ask yourself, where does this break? Why doesn't this, right? We'll get a mathematical, in quotes, I guess, answer. We'll get an answer for x and an answer for y. But why doesn't that mathematical answer provide an answer to my application problem? You might actually be able to guess why, but go through the exercise and try to figure this out. Try to figure out why, if I just plug in 0.08, I intuitively understand that I shouldn't get an answer. The math will give me an answer to give me a value of x, a real number x and a real number y. Why doesn't that solve the application problem? Okay, so we'll go really quickly through this problem on the worksheet side of things. It's a similar problem. Trying to zoom it in here. There we go. Peanuts sell for $5 a pound. Cashews sell for $8 a pound. How many pounds of cashews should be mixed with 14 pounds of peanuts to obtain a mixture that has a value of $5.90 per pound? Similar type of problem to what we just did. It's a little bit more straightforward. So let's take maybe 3 minutes or so, work through this one, and then we'll come back and we'll work through it, and then we'll move on to geometry problems.
Wait, this is like doable?
Yes.
I'm just looking at it and I feel so stupid.
You're not. I actually did one of these problems in the math cafe, so I know it's doable, unfortunately.
I'm just
Yeah.
I'm just like, what do you mean you can, like, I guess.
Yeah, this is doable
Oh,
because
never mind. My brain has connected the dots.
okay, yeah. If anybody's struggling to get started, take a look at the mixture problem we just did, and that should give you some clues. Yeah. Okay, so let's take a look at this one. Well, yeah, peanuts are $5 per pound, and cashews $8 per pound. We want 14 pounds of peanuts. Geez, I like can't spell today. 14 pounds of peanuts, and not really sure how many pounds of cashews. And I want this mixture to be $5.90 per pound. Question in chat, let's see. Okay.
Sorry. That was very important. I was just like,
Okay.
oh,
No.
I understand, because it's not, you wouldn't just do like, because if it's $8 a pound and $5 a pound, you just wouldn't have a full pound per pound. Like it would be like the mixture. And then I realized that I had no idea how to actually reduce it, so it was the mixture of 1 pound.
Yeah, that's an important point is, yeah, it's not necessarily going to come out to be a whole number. It might, but we could say we need to mix 14 pounds of peanuts with 7.3 pounds of cashews, and that would be a fine answer if we got something like that. Yeah, this is a question mark, not a 7, but okay, so let's just start using P for peanuts and C for cashews. So what would I have? I'd have a mixture that has a total weight of P plus C. At a cost of $5.90 per pound. So on one hand, the total cost of a certain mixture is going to be P plus C times 5.90. On the other hand, I can break it into its component costs. The peanuts cost $5 a pound. So 5P is the cost of the peanuts that are in the mixture, plus the cashews at $8 a pound, plus 8C for the cashews. And this is where that similarity with the acidity comes in. We have kind of the amount of acid, the amount of acetic acid from the cooking vinegar. Wrong one. The amount of acetic acid from the cooking vinegar, the amount from the cleaning vinegar, and then the acidity that we want times the cooking plus cleaning vinegar volumes. So that's where that kind of similar feel comes in. Okay, but we also know, so this is what we want. There are going to be lots of, I guess, choices of P and C that will solve this, right? If I put in, let's say that maybe one solution was 1 pound of peanuts and 2 pounds of cashews or something. Well, then if I put in like 2 pounds of peanuts and 4 pounds of cashews, that would be a mixture with that same unit price, that same dollars per pound. Since I don't have a constraint on the actual amount of mixture that I want here, I don't have a constraint on P plus C explicitly. It is a little bit different than my previous problem. Before I said I wanted a total volume of a certain amount at a certain acidity. Here I'm basically just starting with saying I want a certain price for the mixture. But I do have one more constraint, and that constraint is I want a total amount of peanuts of 14 pounds. So my kind of, in a sense, second equation here really is just the trivial equation, P equals 14. So that's what makes this problem a little bit easier than this previous one. Here I would have like P plus C equals something. But here I have a simpler second constraint, right? If I had rephrased this to say, instead of 14 pounds of peanuts, if I said how much of each of these should be mixed to make a total mixture of 14 pounds with a value of $5.90 per pound, this would be almost exactly the same problem as the one we did before. But this second equation is basically a trivial equation. I just plug in, P equals 14. So I have 5 times 14 plus 8 times the amount of cashews in pounds equals 14 plus amount of cashews times 5.90. I think at this point, maybe I'll multiply both sides by 10 just to make this 5.9 go away. So I'd have 50 times 14 plus 80C equals 14 plus C times 59. I don't know if this really got me a whole lot, but at least I don't have the decimal point, that I'm trying to keep track of. Okay, 50 times 14, that's 700. How do I do that quickly? Well, I recognize, sorry, my allergies are just like driving me crazy today. I recognize that 14 is 2 times 7. 2 times 50 is 100, which is easy to multiply by. So I get 700 from there, plus 80C equals, and then I'll do 14 times 59 on the calculator, 826 plus 59C. And at this point, I have one equation and one variable, C, the amount of cashews. And I'll go through my equation solving steps. Minus 59C from both sides. That gets my variable terms on the left. Let me get my constant terms on the right. I'll do that by subtracting 700 off of both sides. 80C minus 59C is 21C. These go away, equals 126. Or I get, after dividing by 21, C equals 126 over 21. I know that there's a factor of 3 in 21, it's 7 times 3. I also know that there's a factor of 3 in 126. I know that I could think through it and say, okay, well, 3 times 40 is 120. That gives me 6 left over, and 6 is 3 times 2. Or I could use my my division trick where I add up the digits. 1 plus 2 plus 6 is 9, and since 9 is divisible by 3, 126 is divisible by 3. So this is going to be 3 times 42 over 3 times 7. I can divide out the 3's, and I can also note that 42 is 7 times 6. I can divide out the 7's, and I end up with C equals 6. So I need to mix 6 pounds of cashews with 14 pounds of peanuts to get a mixture that is $5.90 per pound. So the big challenge here was really coming up with this equation. And, once we get this equation, plugging in 14 pounds for peanuts, and then solving the resulting linear equation to get 6 pounds of cashews. And like I said before, there would have been nothing really wrong if we had gotten, 7.8 pounds of cashews or something like that. And maybe as a little bit of a hint to the previous exercise, I could have a mathematical equation where the answer was like C equals -12. That would be a fine mathematical answer. But if I had to mix -12 pounds of cashews with 14 pounds of peanuts, yeah, maybe I wouldn't be super satisfied with that answer to the application problem. So that's a pretty big hint to the exercise that I mentioned here, figuring out why the mathematical solution to this might not satisfy the actual application. Okay. So moving on to 3.4. Here we're working on solving geometry applications, particularly applications with things like triangles, rectangles, and squares. So a couple things to just recall about these objects. In triangles, if we have 3 angles, maybe call them A, B, C. The sum of these 3 angles has to be 180 degrees. That's just basically a rule about triangles. So we can think of this as a formula. We can manipulate this formula as needed to answer some of our problems later on. A right triangle is a triangle where one of the angles is 90 degrees. We denote that angle. A 90-degree angle is like a perpendicular meeting of the 2 lines. We denote that angle with a little box, which I can't seem to draw a horizontal line. There we go. We denote a 90-degree angle with a little kind of box in the corner like that. This would be a right triangle. Something else to always remember about geometry applications is when we draw the pictures are not assumed to be to scale. So the longer side and the shorter side might not look longer or shorter in the picture, or a 30-degree angle might not look exactly like 30 degrees if you measure it with a protractor. So we need to keep that in mind, that these pictures that we're drawing, these triangles or rectangles, are more diagrams than they're more meant to be diagrams than faithful representations of what's going on. Now, if we do have enough information to draw a more faithful representation, we usually should try to. That gives us a better kind of gut feeling about whether our answer is right or not. But a lot of times we'll be trying to solve for, say, the length of one of the sides. So we really won't know at the outset how long that's going to be, or whether it's going to be the longer side or the shorter side, or what. So when we draw these diagrams, they're more pictographs, they're more diagrams than they are faithful representations of the actual geometry. The Pythagorean theorem says that for a right triangle, the 2 sides that are adjacent to the 90-degree angle, we call those the legs. I just cannot draw on this today for some reason. I don't know what my issue is with my trackpad over here. There. So the 2 sides that are adjacent to the 90-degree angle are the legs. The side that's opposite the 90-degree angle is the hypotenuse. We couldn't have figured out something shorter to call it. And quite often we call the lengths of the legs A and B, and the length of the hypotenuse C. And the Pythagorean theorem says, importantly, for a right triangle with leg lengths A and B and hypotenuse length C, A squared plus B squared equals C squared. 1 second. Sorry, I just had to sneeze there. Didn't want to blow all of your ears out. So this is the Pythagorean theorem. The sum of the squares of the legs equals the square of the hypotenuse. And again, that's only for a right triangle. That doesn't work for triangles in general, just right triangles. And then lastly, perimeter versus area. For a triangle, if we have side lengths A, B, C, the perimeter is A plus B plus C. For a rectangle, if we have side lengths, let's say L and W is what we often use for rectangles for something like length and width. The perimeter, the rectangle is actually a little easy to mess up the perimeter on, because a lot of times, because of all of these 90-degree angles, we know that the width of the top is the same as the width of the bottom, and that the length of the right side is the same as the length of the left side. So a lot of times we just label, say the bottom and the right side or something, and we don't explicitly label the top and the left side. So it can actually be pretty easy to mess up the perimeter on the rectangle and just say something like L plus W, because that's all that we really see. But remember, perimeter is like if we started at some point on the shape and walked all the way around, got back to that same point, we'd have to traverse left to right and then right to left, also bottom to top and top to bottom. So it's actually 2L plus 2W. Again, really easy to make a mistake here and just say it's L plus W, because we usually don't label all 4 sides of a rectangle. Usually we just label 2 sides. But if we explicitly label all 4 sides, we see pretty clearly it's 2L plus 2W. The area of a rectangle is length times width. The area of a triangle is a little more complicated. We have to find the height of the triangle with one of the sides kind of laying flat. So I pick a side, I lay the triangle flat on that side. In this case, maybe side C. We've kind of laid it flat on side C. And then we can find the height of the triangle. Now, the height isn't like the distance A or the distance B. It's this distance here. And that's kind of a geometry or trigonometry problem to find that height for a given, arbitrary triangle. So that's beyond the scope of this course to find that height for a non-nice triangle. The thing that we've laid it flat on, we call that the base. And the area for the triangle is 1/2 times the base times the height. Now, something that's kind of nice is if we had a right triangle and we choose to lay the triangle flat on one of its legs, not on the hypotenuse, but on one of the legs. Let's call this A, this B, and this C to stick with our same notation from up here. Well, with a right triangle, nicely enough, if I lay the triangle flat on one of its legs, on one of the sides adjacent to the 90-degree angle, that's the base, then the other leg is actually the height because of that 90-degree angle. That actually helps us a lot. So the area for a right triangle is just 1/2 times the product of the two legs' lengths. Okay, so hopefully none of this is like really new, earth-shattering material, but this might be something that you haven't seen in a little while, and dusting off the cobwebs is always a little helpful. So let's get into a couple of examples, and let me change the color in here. There we go. So first example, the measure of two angles of a triangle are 170 degrees or 107 degrees and 32 degrees. Find the measure of the third angle in degrees. So if we look at our array of formulas up here, we're dealing with a triangle, so we're not going to use the rectangle formulas. And I see that I'm interested in knowing what one of the angles is. And the only formula I really have that relates angles to one another, all of these formulas down here relate side lengths to one another. But the only one that relates angles to one another is this one. The sum of the three angles is 180 degrees. So A plus B plus C equals 180 degrees. And we can say maybe, we'll call angle A 107 degrees, angle B 32 degrees. (107 degrees) plus 32 degrees plus C, the angle that we're looking for, is 180 degrees. These are like terms. They are numbers with the same unit. So I can combine these together and get 139 degrees plus C equals 180 degrees. And now I want to isolate the variable term. I do that by subtracting 139 degrees off of both sides. I don't know what my deal is. My trackpad is like skipping or something when I try to write. Maybe I need to restart my computer. I'm really bad about that. I just keep my computer on for like a month at a time and never restart it. So, and then 180 degrees minus 139 degrees, well, 140 to 180 would be 40 degrees. And then I need to go one more. So I can use this formula, plug in the pieces that were given to me in the problem statement, and then use my equation solving strategy to solve the equation for the variable. And I get 41 degrees for my third angle. Now you might have been able to work through this without, officially going through the formula. That would be fine. But you could go back to the formula if you needed to. Okay, so take a minute or so to go through this one. If you want to work ahead, the next one will be on the screen as usual. So we'll take about a minute and then we'll come back. This should be a pretty straightforward one. Okay, so we have a triangle, so 3 sides. We're given 2 of the side lengths, 7 feet and 8 feet. We're told the perimeter is 21 feet. How long is the third side? We know the perimeter can be expressed in 2 different ways. It can be expressed as the sum of the 3 side lengths, or it can be expressed in terms of what was given in the problem statement, that it's 21 feet. Those two have to, they represent the same thing, they have to be equal. We get 15 plus x equals 21. Subtract 15 from both sides, we get x equals 6. And what's the unit going to be? It's going to be feet. So we need 6 feet for the third side. Okay, how do we see that it's in units of feet? All of these are in units of feet, and we just subtract feet minus feet on the right-hand side. We're left with units of feet. Okay. Okay, so now let's consider a right triangle. So that's an important piece of information. It's a right triangle. One leg has length 12. In other words, one of the sides that's adjacent to the 90-degree angle, not the opposite of the 90-degree angle hypotenuse. It has a hypotenuse with length 13. And we want to compute the length of the other leg. So let's draw a diagram. We have a right triangle. One leg has length 12. I'll put my 12 on the left side. If you wanted to put your 12 on the bottom leg, it wouldn't matter. We just don't want to put the 12 on the hypotenuse on the side opposite the 90-degree angle. The hypotenuse has length 13. What's the length of the other leg? Let's call that x. My Pythagorean theorem says that the sum of the squares of the 2 legs is equal to the square of the hypotenuse. In other words, 12 squared plus x squared equals 13 squared. Now, at this point, I might be a little nervous. I might look at this and say, oh, I've got an equation, okay. But it's actually not a linear equation. I have x squared showing up. So I might be a little nervous at this point, but let's go through those similar equation solving steps and just see what we get. Let's just see what happens. Well, instead of 12 squared and 13 squared, let's write out what those are. 144 plus x squared equals 169. If instead of x squared, if this was like 2 times x, how would I proceed? Well, I still have these same general ideas. I still have a variable term, a constant term, and a constant term. Again, this is really the power of mathematics. I can abstract away from those linear equation solving techniques, but I can still follow the same pattern. Can I isolate the variable term? I mean, this isn't strictly a linear equation, but could I follow a similar pattern? Could I get the constants onto the other side? What's 169 minus 144? Well, that's 25. And at this point, I might say, where do I go from here? Well, I'm looking for a value that I can put into this equation for x that will yield a true statement. And I think I can probably guess x equals 5, right? 5 squared, 5 times 5 is 25. I get that just by guessing the answer. So that's one approach. Another approach is just kind of like how multiplication is related to division. Subtraction is related to addition. Squaring something, taking a number and squaring it, to kind of undo that process, we do something called a square root. And this should be reminiscent from, some of the more advanced material in some of the prerequisite courses. But we have this like little funny symbol, the square root of 25. And we'll be dealing with square roots and things more later on in the course. But for now, all that we need to be able to do is to come over to our calculator. And above the x squared button here, kind of catty corner to the 7, there's an x squared button. So if I did like 5 and then hit the x squared button and hit enter, it would give me 25. If I want to undo that process, if I want to go the other direction, I can do second, the second yellow button up here, and then the x squared button. So when I hit second, that says when I hit this button, choose the yellow function that's kind of printed on the calculator near that button, the square root sign. So square root of 25, and that gives me 5, which is exactly what I'm looking for. If this was one that wasn't so easy to guess, square root of 23, well, I don't recognize that as a nice square. I might get an answer like this. Square root of 23 is approximately, what would that be, 4.8 or so. So if I had ended up with, instead of a nice, as we call it, a 5, 12, 13 triangle, one of the special Pythagorean triplets, if I had ended up with one that was not so nice and resulted in me getting x squared equals, say, 23, my solution would have to be an approximate one, x equals square root of 23, or about 4.8 feet. But in this case, we got one that was nice. The third side would have to be 5 feet. When you see something at the end that says rounded to the nearest tenth, especially in WebAssign, that's kind of a hint that the result probably isn't going to work out to be a super nice round number. So, you might expect to get a number that's not such a nice number. So work through this one, take a few minutes, maybe 2 minutes, and then we'll come back and work through it together. Okay, so for this one, we have a right triangle. Both legs have equal length of 3. So both legs have side length 3. We want to find the length of the hypotenuse for this right triangle. Since it's a right triangle, Pythagorean theorem applies. The sum of the squares of the lengths of the legs, so 3 squared plus 3 squared, equals the square of the length of the hypotenuse, x squared. Each of the 3 squareds is 9. 9 plus 9 is 18. So x squared is 18, or x equals square root of 18. Again, we don't recognize this as a nice perfect square. 18 is between 16 and 25, which means my answer should be between 4 and 5. So let's come over to the calculator and do second square root of 18. And this gives me about 4.243 or so, or rounded to 1 decimal place, the nearest tenth, about 4.2. Okay, so the next problem, the area of a rectangle, 256 square feet. The width is 32 feet. What is the length? So let's say that left to right we'll call the width. That's 32 feet. We're not sure what the length is, but the area is 256 square feet. So that's the area inside here. But I know that the area of a rectangle is length times width, or that 256 equals the length. I'm not sure what it is, but the width is 32. I'm looking to solve for L. I divide both sides by 32. I see that both of these are even numbers on the top and bottom, so I can divide a 2 out from both of them. 256 over 2, well, 250 over 2 would be 125. So I think that's 128. Again, both even numbers. 16 over 2 is 8. 128 over 2. 120 over 2 is 60. So I think this is 64. Okay, and I recognize that 64 is 8 times 8. So my length is going to be 8. The units are going to be feet. And let's check the units. My area was in square feet. My width was in units of feet. When I divide, I get square feet over feet. The unit of feet on the bottom divides out one of the units of feet in the square feet, leaving a single unit of feet. So I went back and checked my units as a way to check, and my units seemed to work out. Again, in these application problems, there's often just a ton of context that we can use to check whether our answer is reasonable. And we should leverage that. So we see that, going back and checking the units would be one approach, and we see that that confirms what we expected. The length, of course, should be in terms of feet, and we get it in terms of feet. If we had made a mistake and we did like 32 equals L times 256, when we attach the units, we'd end up with all kinds of wonky units. We'd be claiming that the length was, some amount of 1 over feet. And, we'd have a feet left in the denominator, and that wouldn't be right. Okay, so again, let's take just maybe 3 minutes for this. Go through this problem, take 3 minutes. And again, if you finish early, you can work ahead if you want to. Okay, let's talk about this one. So the problem statement, the width of the rectangle is 2 meters less than the length. The perimeter of the rectangle is 58.3 meters. Find the dimensions, in other words, find the length and width of the rectangle in meters. So one thing that's kind of nice about problems like this, geometry problems, is that there's often kind of a visual method of approaching the problem, the kind of geometric approach, and there's often also an algebraic method of approaching the problem, the more kind of formula-based approach. So there's a sense in which I don't need to know anything about the picture at all if I have the list of formulas. I could say, okay, perimeter, the formula for perimeter is 2L plus 2W. And I'm told the perimeter is 58.3. So I get this equation here. I'm also told that the width is 2 meters less than the length. So width is length minus 2, giving me this equation here. I can then, this W up here that's multiplied by the 2, I can then swap that out for L minus 2. That yields this equation here. That's kind of the more algebraic approach, just applying the formula and going through the algebra. I could also take a more geometric approach, looking at the pictures instead. I could draw myself a diagram of a rectangle. It has width W, length L, but I know that my width is 2 less than the length. So width is length minus 2. That means that I have one side that's L. The other side, in this sense, then is 2 meters less than that one, L minus 2. And if I, were to start at some point and walk my way around, I see that I'm going to encounter 2 L's and 2 lots of L minus 2. I can get to the same equation from 2 different perspectives. This is actually a pretty powerful tool in math, really throughout your entire mathematical career. Is if you have a geometrically linked scenario, I suppose, being able to jump back and forth between the geometric side of things and the algebraic side of things is extremely powerful. Sometimes you go a little bit in on one of the ways. Maybe you approach it geometrically first and you get a little stymied somewhere, but then you can jump over and follow the algebra the rest of the way, or vice versa. Start with the algebra, get a little stuck, and then say, oh wait, I could interpret this geometrically instead, and that takes you the rest of the way. Or maybe you start off thinking about it geometrically and that just doesn't work at all, and the algebra takes you the whole way, or vice versa. So recognizing that in problems where there's an inherent geometric link, thinking about it kind of pictorially versus algebraically are 2 different ways to think about the same problem. And sometimes one or the other way works easier. But either way, we get to this equation. And at this point, we just have a regular old linear equation in one variable. We multiply out the left-hand side, combine like terms, simplify everything. We isolate the variable term by adding 4 to both sides. We isolate the variable by dividing by 4. So 62.3 over 4. I know it's going to be a little more than 15, but that's going to be kind of annoying to work out. I'll jump over to my calculator to do that. $15.575. Intuitively, I know that this length should be in meters, and I think everything works out here, right? This length is in meters, this width is in meters, 58.3 is in meters. I can see pretty clearly that everything is going to work out. These 2's that are multiplying the length and the width, those are just counting numbers because I encounter length 2 times. So it's not like, 2 seconds or something like that. It's just the number 2. So I can see the units are all going to work out just fine. Keep going to that wrong one. Okay, so last problem. So here we have a more of an application-based problem. Brian borrowed an 18-foot extension ladder to use when he paints his house. If he sets the base of the ladder 6 feet from the house, how many feet up the side of the house will the top of the ladder reach? Okay, so let's draw a little diagram. Here we have a house that looks like a very happy looking house, I guess. I don't know. So we have a house. We have a ladder on the ground. The ladder has length 18 feet. The house, maybe not my house that I've drawn here, but the house should be hopefully perpendicular to the ground. So the walls of the house are going straight up and down vertically, and the ground is horizontal. And the base of the ladder is 6 feet from the house. And our question is, what is the height up the side of the house that Brian can reach? He wants to know if that the ladder is going to be long enough for him to paint the whole house. We can reinterpret this as a geometry problem, looking at a triangle, specifically a right triangle, where that 90-degree angle is where the house meets the ground. The bottom side is going to have length 6 feet. The hypotenuse 18 feet. Again, not being super concerned with scale here. And then the height of the triangle, h. I'm trying to find a side length. Remember, these aren't angles, so that sum of angles formula doesn't apply. Well, Pythagorean theorem connected the side lengths. Can I apply the Pythagorean theorem? Yes, because I have a right triangle. That was the condition of the Pythagorean theorem. If we have a right triangle, Pythagorean theorem does apply because we do have a right triangle. My legs are length h and 6 feet. And my hypotenuse is 18. This gives me h squared plus 36 equals, and I'll come over to my calculator and do 18 squared, 324. Again, I have an equation that's actually a nonlinear equation. It has this h squared in it. That might make me a little nervous at first, but I say, well, I still do just have the same structure. I have a variable term, a constant term, a constant term. Can I isolate my variable term? Can I go through the same pattern that I use to solve linear equations, even if this isn't a linear equation? Will the same pattern help me move forward and make progress? Right? Again, this is the power of mathematics, where we can abstract away from the details, recognize that underlying pattern, try to apply that underlying pattern to a different but seemingly related problem, and here that will help us. (324 minus 36), I think that's 300 minus 8, or 292. I don't recognize 292 as a nice perfect square. Like if I had gotten h squared equals 100, I'd know that h was 10. So I'm just going to come over to my calculator. And remember that the related equation to this is that h equals square root of 292. That's just something that we plug into the calculator. Second x squared gives me the square root symbol, 292. And this gives me 17.088. We're rounding to 1 decimal place. So h is about 17.1. We know that h should be measured in feet. Let's check our unit and make sure that everything worked out okay.
I got
6 is
288 for h squared.
for
Yeah,
4 minus 36.
yeah.
Ah, yeah. Okay, so 288.
It's those allergies. No, I'm just kidding.
Yeah. Yeah, I was just checking to see if you're paying attention. No, yeah, thank you for pointing that out. Yeah, just a brain fart on my end. I think I did 320, was it 326 minus 34? Maybe I got the 6 and the 4 backwards. Yeah, thank you. 288. And then what's square root of 288? 16.97. So if we round this to the nearest tenth, 16.97, then 0.9 rounds up, bumping our 9 up to a 0, and then 16 up to a 17. So 17.0 feet. Yeah, thank you for pointing that out. So make sure that you get that correction.
I'm just glad I'm not the only person that makes these silly mistakes.
Oh no, we all do it. So it's so easy to make little mistakes like that. And yeah, thank you for pointing that out. Let's check the units. Oh. So 6 is in units of feet. So 6 squared is in units of square feet. 18 squared is in units of square feet. That means that h squared, which is the difference between two things that are in units of square feet, is going to be in square feet. When I do h equals square root, I can also put the unit under that square root. So I'm square rooting the number 288 to get approximately 17. I also will end up square rooting the unit. The square root of feet squared does give me feet. So I can go through and check my units. It was a little more complicated here because my unit got squared and then square rooted. So I had to be a little more careful with tracking everything, where everything went. But I do see that my units worked out okay. Again, I can use that context to check my answer. I also ended up with a positive number. That's probably good. Like if I ended up with a negative number, that would have been suspicious. I also ended up with a number less than 18. From context, I mean, if I have an 18-foot ladder, if it was perfectly straight up the side of the house, if a couple people were pushing it against the side of the house while I climbed it, it would reach 18 feet up. Right, if the ladder was like this, h equals 18. But if I kick the base out, that's going to move the height down a little bit. I can just imagine that happening. I certainly should not get in a height above 18. My height should be below 18. And indeed, it is below 18. If I had gotten a height of 26 or something, that would have been a positive number, but that would have been bigger than 18. I would have been, again, suspicious of my answer. So if I had been a little more wrong, instead of getting a number like 17, that does kind of, or 17.08, does kind of still fall into that reasonable territory. If I had made a mistake and did square root of 392, I'd have got a number that's bigger than 18, and then I'd have recognized that, right? So these checks, they're not going to catch every mistake. Like this mistake would have made it past all of these checks and I wouldn't have caught it, but they'll catch some mistakes. So we know from context, it's got to be a positive number, less than 18 in units of feet. That all checks out. Okay, in the last 8 minutes or so, let's take about 4 minutes to work through this problem. We'll come back, we'll talk about it. And then we'll save this last problem for next time. But work through this problem, and then why won't it let me unselect anything now? It's just not a good tech day. All right, so work through this string of lights problem, and then if you want to work ahead, you can look at the next one.
I'm sorry, but didn't the class end at 10:10?
Oh, thanks for, I lost track of time, so thanks for pointing that out. It's just not my day-to-day, I guess. I don't know.